So recall in the last lecture, we talked about how to model logic decisions, right? How do you translate from logic propositions to mixed integer linear programming constraints? So in the next few lectures, we will talk about applications of mixed integer programming and some algorithms. But before we even talk about applications, I want to give you some conceptual overview on what is a good formulation for mixed integer linear programming. Right? So for a given problem, there might be different ways of formulating them into mixed integer linear programming constraints. So what would be a good formulation? Right? Among different formulations, which one is better, which one is worse? So that's what we will talk about in this lecture. And at the end, we will introduce a concept called total unimodularity. It is related to what is a good MLP model. Okay. But before we talk about what is a good MLP model, I need to give an overview of the algorithm to solve mixed integer linear programming, right? Because you need to have a basic understanding of an algorithm to really appreciate what is a good formulation. And then we will talk about this branch and cut algorithm in detail, right? So branch and cut is basically combining what is so-called branch and bound with cutting planes. We will spend one lecture just on branch and bound and one lecture just on cutting planes. But before that, I will give you a very superficial overview of the branch and cut algorithm so that at least you have some geometric overview of how the method works. Yeah, so recall this is a problem formulation we are dealing with, right? We have linear objective, linear constraints. Some of the variables are continuous, some of the variables are integer. In this class, we will just assume all the integer variables are 0, 1 variables for the reason I talked about in the last lecture, because most of the integer variables are used to represent logic decisions, either 0 or 1. Right? So how do you solve MLP? Right? If you ask a pure mathematician, they will be wondering why would someone work on mixed integer programming algorithm? Because they will tell you the solution is finite. Right? You just enumerate all the possible combinations of the binary variables and solve the corresponding LP. Right? They are 2 raised to the power of n2 linear programs if you want to enumerate all the possible binary combinations. Right? It is a finite number when n2 is finite, but this number can grow very fast when you have a large number of binary variables, right? Even if you have, let's say, 100 binary variables, 2 raised to the power of 100 is an astronomical number, right? So in practice nowadays, the state-of-the-art commercial solvers can solve problems in the order of 1 million variables. So 2 raised to the power of 1 million is a prohibitively large number. But why the algorithm is so good that it can solve this type of problem, right? As I said, the algorithm to solve MLPs are called branch and cut. Before I explain what branch and cut is, we need to talk about something called branch and bound. You can think about branch and bound as a smart way of enumerating all the binary variables. Instead of enumerating 2 raised to the power of n2 variables, they solve this problem in a trial and error way. Okay. So in a branch and bound algorithm, it starts with something called linear programming relaxation. To explain this better, I'm using pure integer variables. But then in practice, we are mostly dealing with binary variables. Right? So you can think about this as an integer linear program where all the variables, x1, here it's in 2D, right? x1 and x2 are integer variables subject to some continuous constraints. Right? The continuous constraints are described by the boundary of this polyhedral. Right? Now, when you solve the so-called linear programming relaxation. The idea of linear programming relaxation is to say, let's ignore the integer constraints for now. Right? Just assume there are no integer constraints. We are only dealing with linear constraints. Right? So essentially, you are solving a linear program with the constraints specifying the yellow area in the figure here. Right? Okay. But the unlucky thing is, the linear program's optimal solution is at one of the vertices. Right? So now there are how many vertices here? 4 vertices in this polyhedral set, right? But none of the vertices correspond to an integer point. Right? They all correspond to some fractional point. These black dots are the integer points here, right? So if you solve the linear programming relaxation, you hit this point here. This point is a feasible point for the linear programming relaxation, but it's not feasible for the original problem with the integrality constraints. Right? But you can start from there. The nice thing about the linear programming relaxation is that it gives you a lower bound of the original problem if you are minimizing. Right? So why it is a lower bound? Yes?
Well, it's a lower bound because if you relax that constraint, then you're going to find something that's in the middle that's actually not discrete, and the discrete can only be as good or worse than that because you're adding constraints.
Right, exactly, right? So the short answer is the linear programming has removed all the integrality constraints. Right? If you are removing some constraints from the problem, you should be able to get a better solution than with those constraints, right? So that's why if you are minimizing the LP relaxation, we'll give you a lower bound, right? And as we know in any algorithm, if the upper bound and the lower bound are equal to each other, then we can terminate, right? So here is basically in a branch and bound method, we need to deal with 2 questions. First is how do we improve the lower bound such that it can move to the move up, right? And the other question is how do you find good feasible solutions, right? With the LP relaxation, we are not even finding a feasible solution to the original problem since the integer constraints have violated. Okay, so in branch and bound method, the idea is we will solve the LP recursively over the so-called non-integral variables. Right? So if some of the variables are not satisfying the integrality constraint, we will do this operation called branching. Okay? So the idea is you will split one problem into 2 problems. On one side of the problem, you will say xi has to be less than equal to xi star floor, right? So this is rounding down the number. And the right-hand side is rounding up the number, right? Okay, suppose x star is the solution to your linear programming relaxation. Right? You could pick a non-integral variable and then split the problem into 2 parts. Okay, that's called branching. Then we can get upper bound and a lower bound among a branch and bound method, where the lower bound is so-called the minimum among all the leaf nodes. We will see that in a second. The upper bound is the minimal among leaf nodes with integral solution. Right? So you probably cannot visualize it in this slide, but I will come back to this later. So when should we stop? Right? One of the things we may find is that when the problem has finite optimality condition, then you have L equals to U. Right? This is like an optimality certificate. Sometimes you may get infeasibility certificate when you find out the lower bound is minus infinity. Right? Plus infinity. Right? So if lower bound is plus infinity, you solve the LP and you are minimizing it's infeasible, then you could just prove the problem is infeasible. Also, you could also terminate by some threshold. There might be some typo here. So what you could do is you check L minus U, right? If they are, for example, less than or equal to a tolerance epsilon, then you can terminate. Right? You don't need to have L strictly equal to U. Now, let's use this figure to visualize how a branch and bound method works. Right? Remember at the root node, we got a fractional solution. Right? Remember, if you draw the whole figure, right? So this solution is what we got at the root node. Right? It's a fractional solution. Now what you can do is you do some branching on variable x2 and split this problem into two parts, right? You know this point is integer infeasible, right? So now let's say x2 has to be greater than or equal to the integer round up, and here you also round down this number, right? So now you basically split the problem into two problems, right? By branching the problem into two problems to round up and round down a fractional variable, right? So with that, you can represent these two problems as two nodes in this in a tree data structure. Right? So here, this is your root node. You find it is integer infeasible. Now let's pick a variable and split the problem into two problems, right? So with these two problems, what is the lower bound of the problem now, right? You can get a bound on, let's say, the left problem, and this is a bound you got. This is the optimal solution for the relaxation for the right node, right? Then what is the lower bound for the whole problem? Right? Yeah, the left one, because the lower bound of the whole problem is the best lower bound you obtain among all the nodes, right? You cannot rule out the solution can be always worse than this, right? So this lower bound is better than the right one. Therefore, the global lower bound is obtained at this left node here. Okay, and now you can repeat, right? So you could let's suppose you pick the right problem to continue branching, right? So which node you pick, it is not a trivial problem. Let's just assume you pick the right node to branch, right? So let's assume in this case, you branch on the x1 variables, right? So essentially you split the x1 variables into x1 less than or equal to something and x1 greater than or equal to something, right? So now this right node is split into two nodes here. Okay, and luckily, what you find out is at this blue node here, right, this particular problem, the optimal solution of this relaxation happens to be integral, right? So now you find a feasible solution to the original problem, since you already branched twice, right? So then this node already satisfies the integrality constraint, right? So this is a feasible solution to the original problem. Therefore, we can claim it is an upper bound. Okay. Yeah, and then you can keep branching. Let's say you also branch on this particular node and then split it into two nodes by branching on one of the integer variables. So as you can imagine, the bounds will keep improving, right? The lower bound will keep increasing, the upper bound will keep decreasing. Right? Now, at the end of the day, you will have the upper bound equal to the lower bound for this very trivial problem. Right? It's in 2D, that's why there are not many nodes here. You already converge. Right? When the upper bound and the lower bound equal to each other, then for this problem you can already terminate. Okay. Any questions regarding the high-level idea? I didn't even show you the pseudocode because I will show you a pseudocode when we talk about branch and bound. Here, this is just a geometric intuition. Right? The intuition is the following: because you cannot satisfy integrality constraint, you will do one operation called branching. Branching means if you have a fractional variable, you split that variable into two nodes, right? One greater than or equal to an integer, one node makes that variable less than or equal to an integer, right? and bound comes from LP relaxation, right? And the root node LP relaxation is a lower bound, right? And after you branch, it's not as trivial. You can solve the LP relaxation at each node, and pick the node that give you the most optimistic lower bound, right? Yes.
When you're going through, is it better to follow a branch all the way and then go back up, do it that way, or is it better to take each branch down to a certain level and then before you move down each route?
Yeah, so that's a great question. So the two ways you describe are called depth first search or breadth first search, right? Well, you should go deep first, or you should expand the tree first, right? So that is not a trivial problem. We will actually discuss about that when we talk about branch and bound. Yeah, but that's a very good question. Yeah. Any other questions? Yeah. Okay. Now, that's what is called branch and bound, right? If you just implement a vanilla branch and bound, solving MLP is still very slow, right? Because in the worst case, you may need to branch out all the variables, right? And then you still get an exponential number of nodes. And this is what so-called cutting plane comes into play. Okay. We won't talk about the theory. I will just give you a geometric feeling of what a cutting plane is. Right? Now imagine you have a linear programs, right, which is denoted by this light yellow area here. Right? So if you solve this LP relaxation, you get this point. Right? This point is a little far from a feasible point. Okay, and then you need to do branch and bound to make it feasible. However, let's assume if you are really smart and you happen to get this dark yellow region here, right? So this dark yellow region is also a polyhedral set, right? You just don't know how to get that. If you happen to get this region here, you don't need to do branch anymore, right? You don't need to branch anymore because for this dark yellow region, all the vertices are integer feasible, right? But the thing is that, of course, we don't know how to get that description, right? So there are actually theoretical ways for any MIOP, there are theoretical ways to get this dark yellow region, which is called the integer Hall of the integer program, right? But getting this convex Hall or integer Hall of all the integer points, it's a very expensive step. Typically, you need exponential number of linear inequalities to get to that integer Hall, okay? So what cutting plane means is you can cut off some chunk of the linear programming relaxation, but then you are not cutting off any integer feasible points. Okay, so for example here, this hyperplane is a cutting plane, right? It cut off this dashed region here. Since no integer points exist in the region I already cut off, right? And then you make the relaxation closer to the integer points, right? So as you can imagine, if you can cut off a significant chunk of the linear programming relaxation and make the feasible region closer to the convex Hall of the integer points, you will only need to do fewer branching steps, right? So if you get the convex Hall of the integer points, no branching is needed, right? But if you do something in between, let's say cut off some part of the linear programming relaxation, you will be able to reduce the number of nodes in branch and bound. Okay, so that's sort of the intuition of why we have cutting planes, right? But how do you derive cutting planes is a very hard problem, right? So we would spend one lecture on cutting planes. Okay, any questions related to this concept? Okay. Yeah. Now, so the idea is you can use cutting plane to so-called tighten the LP relaxation. So this is a verb that is usually used in integer programming research, right? Which formulation is tighter? Okay. then tighter relaxations can reduce the number of nodes in branch and bound. Right? That's why, as you can see, modern solvers on MLP are so good because they combine branch and bound with cutting planes. Right? If you don't have any cutting planes, branch and bound itself can be very slow as well. Okay? Of course, an extreme case is you just get a convex hull of all the feasible points, right? Like this dark region there. Okay, and then you only need to solve a single LP. So now with this overview, you kind of get to know what is branch and bound, right? So branch and cut, right? Branch and bound itself is sort of like a smart way of enumerating all the binary variables. Right? You have an operation called branching. Instead of try to branching all the variables at once, you have sort of like a trial and error step, right, to decide which variable you branch, and then sometimes you can reduce the number of nodes. And cutting plane is something that can be added on top of a branch and bound, right, to reduce the number of nodes. Okay. Now, as you can see with this cutting plane, you may get a formulation that is tighter than the original LP relaxation, right? So because you add cutting planes. But now, let's talk about the a very interesting problem, right? How do you compare two MLP formulations of the same problem? So what do I mean by that, right? As I said, there can be different ways of formulating the same problem using MLP, right? I will show you an example later using the knapsack problem. But here, I first want to talk about some theory related to if I give you two formulations, right? Formulation 1 and 2, which one is better, which one is worse, and in what sense, right? Okay. So let's assume, for the sake of the argument, there is one problem out there, right? And I come up with two formulations. Right? The first formulation involves x and y. Right? So let's assume these two formulations involve the same number of variables. Right? Sometimes they even involve different numbers of variables. It's an even more complicated issue. Okay. So now let's assume the first formulation, we have a1x plus g1y less than or equal to b1, where y is integral and x is continuous, right? And this is the second formulation represented by a2x plus g2y less than or equal to b2y being integral, right? Let's assume if you have y being integral, they represent the same problem, or these two sets are the same, right? And now let's consider their linear programming relaxations, P1 and P2. The difference between P1 and P2 and their original sets are just like you relax the integrality constraint, right? So here this set doesn't have y being integral, right? This first set has y being integral. That's the only difference here, right? So how do you compare these two formulations? Which one is tighter? So we say a formulation is tighter if the LP relaxation of the first problem is a subset of the LP relaxation of the second problem, right? And if their LP relaxations are equal to each other, then we say these two representations are equivalent, right? On the other hand, if these two sets are incomparable, right? Meaning if you take P2 out of P1, or if you take P1 out of P2, they are both non-empty, then the two representations are incomparable. Okay, so what does that mean, right? So this is essential, like you compare the LP relaxation of these two formulations, right? So if you say this is the LP relaxation of the first problem, right? Let's say this is P1, and then let's say this is P2. Right? Py is strictly contained in P2, right? So then you can say Py is a tighter formulation than P2 because its LP relaxation gives you a smaller region, right? When the LP relaxation gives you a smaller region, that means you need to do fewer number of steps in branch and bound. Right? But if you have the two problem looks like this, right? So let's say this is P1 and this is P2. Right? In this case, they are incomparable, right? Because if you remove P2 from P1, essentially, this means the difference of two sets, right? You take P2 out of P1, then you are left with this region here, right? It's a non-empty region. Same-wise, if you take P1 out of P2, then you are left with this region here. It's also a non-empty set. That's why they are incomparable, right? Okay. And if they are equal, then we say these two representations are equivalent. Okay. Again, why are we comparing their LP relaxation? The reason we want to compare their LP relaxation is because when the LP relaxation is tighter, just like in this plot, right? When the LP relaxation is smaller, then you can reduce the number of nodes in branch and bound, right? So therefore, you always want to make the linear programming relaxation set as small as possible. Okay. Yeah. Now, how do we rigorously prove P1 is contained in P2? Right. This is something we have covered this before in a linear programming lecture. Right. So we say when a polyhedral set is contained in another polyhedral set, right? How do we prove that? Okay. So this is something you can do using Farkas lemma or theorem of alternative, which is what we covered in linear programming lecture. Okay. So let's try to refresh our memory. Right? So suppose we want to prove P1 is contained in P2. Right? So mathematically, how do you describe one set is contained in another set? Right? So mathematically, the way you show that is pick any point in the first set and show it is also in the second set. Right? But for a polyhedral set, it's very hard to do, right? Because polyhedral sets are not described by points, right? They are described by constraints. Right? So you cannot show that easily, right? Unless you have some sort of inner approximation of the polyhedral set, right? Convex Hall of extreme points, right? But now since we have this half-space representation, right? So the other way to think about this is if P1 is contained in P2, that means P1 is so-called more constrained than P2, right? So when P1 is a subset of P2, you can argue that P1 is more constrained than P2. Or in other words, every constraint in P2 is implied by the constraints in P1. Right? So again, so if you want to show P1 is more constrained than P2, you can check for each single constraint in P2, it is implied by the constraint in P1. Right? So with that, you can show the constraint in P2 is a result of the constraints in P1, right? When the constraints in P1 hold, all the constraints in P2 must hold, right? So therefore, then you already show P1 is a subset of P2, right? So now the question is, how do you actually show each constraint in P2 is implied by the constraint in P1, right? So that's essentially what we want to show, right? So P1 is contained in P2 if and only if for every inequality, let's denote each inequality in the stat P2 as alpha 2x plus g2y less than or equal to beta, right? So let's just assume this is one of the inequality among these matrix inequality, right? So for each of these inequality, it should be implied by the inequalities in P1, right? So all these constraints should imply each of these constraints in P2, right? So how do we show one inequality is implied by another system of inequalities, right? So that's what we we did in linear programming. This is called the theorem of alternative. Right? Basically, if you want to show why inequalities implied a system of other inequalities, you need to find something like a Lagrange multiplier for the other system inequality. So, you can check Farkas lemma and theorem of alternative. Right? That's why these theorems are still very powerful when you deal with integer programming problem. Right? So this is implied if and only if there exists multiplier u, such that you multiply a by u, right? This could be, should there be a transpose? But yeah, if you consider this as you could consider them as column vectors, right? So if you aggregate all the constraints in A and aggregate the constraint in G, right? So maybe you could even write a transpose here. Okay, then you have U be less than or equal to beta 2, right? So with that, as you can see, after you aggregate the left-hand side, right, let them equal to be A2 and G2, then the right-hand side is less than or equal to, beta 2 here, right? Then that implies this inequality is true, right? So this Lagrangian multiplier is like a certificate to show you this inequality is implied by the system of inequalities in P1. Okay, it's nothing but an aggregation of inequalities. Right? So you could, I will show you an example to help you actually understand what this aggregation means. Okay, but then if you forget about the theorem, you can revisit your notes in linear programming. Okay. Yeah. So now let's consider a particular example, right? And then show you two formulations, and then compare the two formulations. So knapsack problem is one of the simplest problem we've studied, right? Recall the problem is saying you have let's say a backpack with maximum weight B. And there are n types of items you could take where each of the item has a weight AI greater than 0. And then you want to load the knapsack while not exceeding the knapsack capacity B, right? So X has to be 0, 1 variables because that's not allow you to take a fraction of an item into the knapsack, right? And sum of AI xi means the number of items, the total weight of the item you have packed, right? It has to be less than or equal to the capacity B, right? That's just a knapsack problem we talked about before, right? And you want to maximize the total value of the items you packed into the knapsack, okay? Right, so that's one formulation of the knapsack problem, right? And this formulation is very intuitive, right? There is only one constraint. Of course, X is, this is a trivial constraint since X is 0, 1, right? Now, are there different formulations to knapsack? There is a different formulation called a minimal cover formulation. Okay, so this is not as trivial as this intuitive formulation here. So let's first define what is a minimal cover of the set. The definition is the following, right? A subset C of indices, right? So C denote a subset of the indices, right? In total, let's assume you have from 1 to n different items, right? You pick a subset of these items. Now, the set C represents a subset of indices, right? Now, it is called a cover of K if you add all the weights in the set C, it will exceed the capacity of the knapsack. Okay? So if it is it cover and it satisfies this relationship, which says if you remove any of the item from the subset C, the total weight will be less than or equal to B. Right? That is called a minimal cover. Right? So that means if you pick all the items in this set C, it will exceed the capacity. Right? But if you take out any of the items from the set C, you are fine. Right? So that's why it is a cover. It is minimal in the sense that if you take out any of the items, you are within the capacity. Right? That is a minimal cover. Okay. Now, the minimal cover formulation is the following. You have this particular constraint, the sum of all the xi's in the set C has to be less than or equal to the cardinality of C, right, which is the number of items in this set minus 1. Right? And you need to define this inequality for every minimal cover in the set capital K. Right? So how many minimal cover are there? There could be a large number of minimal cover for a big problem, right? So because you need to check every subset of items, right, and find all the subsets that are minimal cover, and then implement this inequality for all the minimal covers. Okay. Okay. So any questions why this inequality has to hold? Okay. Because it is a minimum cover. If you put larger than or equal to the total number of items, it will be bigger than this capacity, right? If you are taking out any of those, then you are fine. Right? So that's why it is less than or equal to the cardinality of C minus 1. Okay. Now, I told you this is a different formulation than the standard formulation, right? That means these two formulations must be representing the same problem, right? So why do they represent the same problem, right? It's not as trivial as that, right? So how do you show these two sets are equal if you have integrality constraints? Right? So if you have the 0, 1 constraint, these two sets are equal to each other, right? Why is that? Okay. So remember, whenever you want to show the two sets are equal, right? You want to show one set is contained in another, and then the other set is contained in the first set, right? Or you could show that these constraints are implied by the constraints here, right? Then you can show that K contains in KC, right? So let's think about how do we show that real quick, right? Maybe let's think about one direction, right? Why this inequality has to hold if we have the knapsack inequalities hold, right? If we have sum of AI, xi less than or equal to b, why the minimal cover inequality has to hold? Any thoughts?
If we take any one more item that from AI will be greater than B
Yeah.
in the cover. So
Yeah, exactly right. That's just the definition of minimal cover, right? If you violate this inequality, then essentially you have this violated, right? That's why if this inequality hold, this must hold, right? Okay. So what about the other way around? Right? If all the minimal cover inequality hold, then this inequality must hold. Okay, so this may not be that trivial, right? So let's show you the proof here. So we already said one direction. This is the first direction is true by definition. Then that the first statement follows easily. And then the second statement, if you assume the x bar is in the minimal cover set, right? Let's consider all the items that equals to 1 in the minimal cover set, right? And let's prove by contradiction. Suppose the x bar violates this inequality, right? So meaning that AI xi bar is strictly greater than b, right? Then you can always find a minimal subset of J such that this inequality is violated, right? Then obviously C is a minimal cover of the original problem. This will violate one of the minimal cover inequality, right? So therefore you can show by contradiction, right? Yeah. This shouldn't be too difficult, okay? Now let's consider illustrative example to absorb this idea a little bit, right? Here we have the knapsack set, right, where each item has a weight of 3, right? And then you have the total capacity being 5, right? Then what are the feasible solutions to this knapsack problem? Right?
One of them is 1 and other 2 0.
Yeah, so you can at most put one of those atoms into the knapsack, right? So you put 2, the capacity will be 6, right? And the minimal cover formulation is the following. You have all the combinations of any of the 2 items, right? Any of the 2 items forms a minimal cover of this set, right? Because each item has weight 3. If you take out one of them, you have weight 3. Then that's fine, right? So this is the minimal cover formulation. And then clearly these 2 formulations are equivalent, as we have shown already. Okay. But then one interesting question to ask is, what about their LP relaxations? Right? Because as we said, the LP relaxation will determine how many nodes you get in your branch and bound method. Right? So let's assume you have 2 formulations of knapsack problem. One is the original formulation. The other is minimal cover formulation. Which one is tighter? Right? So it can be shown for this trivial problem, right? It can be shown generally. Then I will just show you for this very trivial problem to get some idea why one relaxation is tighter than the other, right? So in order to show that, in order to show the minimal cover is tighter than the original formulation, again, the idea is we need to show P superscript C is more constrained than the original relaxation, right? In other words, this inequality constraint should be implied by these 3 inequalities, right? So how do we show that, right? So let's just do a very simple operation, right? Let's sum up over all these 3 inequalities, right? Just sum them up. And what we got is 2 times x1, 2 times x2, 2 times x3 less than or equal to 3, right? So this implies 3 times x1, 3 times x2 plus 3 times x3 is less than or equal to 5, right? Why is that? Because you could multiply both sides by 1.5, right? Right? So if you multiply both sides by 1.5, you get basically the same left-hand side as this original inequality, right? Yes?
Can you explain again why all of those are less than 1 in that formulation?
In
that
that.
x1 plus x2 is less than 1. Like, why do we know that it needs to be less than 1?
Oh, yeah. So because any of these 2 items, by definition, they form a minimal cover, right? Because let's say if you pick x1 and x2, both in the knapsack, right? So then the total weight will be 6, right? Each weight is 3, right? And it will exceed 5, right? But if you take one of these 2 items out, right? Take x1 out, then x2 has a weight of 3. You are fine, right?
So then, I can understand that for this problem, but how would you know what the right-hand side would need to be for something that's more complex?
Yeah. So that's why it shows you this constraint. The sum over the minimal cover has to be less than or equal to the number of items in the minimal cover minus 1, right? So if you have 10 items in the minimal cover, right, then the right-hand side is 9. Right? Because if you add all the 10, you exceed the capacity. But if you remove one of those from the 10 items, you are good. Right?
So in this case, our minimum cover is 2 instead of 2 minus
Yeah,
1.
yeah, exactly. Yeah. Okay, yeah. All right, so now let's continue, right? So here, as you can see, you can derive some inequalities that are even tighter than the original one, right? You multiply each of these inequalities by 1.5 and add them up, right? Essentially, the left-hand side will all be the same as the original left-hand side, but the right-hand side equals to 4.55, right? Since 4.5 is even smaller than 5, and then now you derive an inequality that is even tighter than the original one, right? So the idea of this Farkas lemma or theorem alternative is you find some weights to the original inequality constraints and add them up, right? And if you can add them up and derive an inequality that is tighter than the ones you want to show, then that means that inequality is implied by this system of inequalities here, right? Okay. So again, if you want to go back to this theorem and try to think about that, right? So if you want to show this single inequality here is implied by the system of inequalities here, then what you can do is pick some weight, right? So imagine this vector u is a weight for each of the inequalities, right? It's like the 1.5 in the knapsack problem, right? You assign a weight to each of the inequality, aggregate them, and then you find out the left-hand side will be equal to the inequality you want to show, and the right-hand side is something even tighter. Then you will be able to show this inequality is implied by the other. Okay. Now, so now we show that PC is contained in P, right? Now, when you say PC is contained in P, you may also wonder, is the inclusion strict, right? You only show one way, but then in order to show it is a strict subset, then you only need to find one single point that is in P, but is not in PC, right? So for example, you can check this point 1, 2 over 3, and 0. It is in the original set P, but not in PC. Okay, yeah. So that's sort of the idea we can have. Okay. Any questions here? Right. So until this point, this is a quite important concept in integer programming, right? If you have two formulations, how do you compare these two formulations, right? If they are using the same number of variables, how do you say one formulation is tighter than the other, right? The idea is you can show the second formulation implies all the constraints in the first formulation, right? Then the second formulation will be tighter. Okay. Yeah. Yes.
In the second formulation, we need to know the set C.
Yeah.
But there can be multiple combinations of variables which will form the set C.
Yeah.
So how to know that how many combinations are possible?
Yeah. So that's a very good question. As you can imagine, to find all the minimal covers, right, it is a very expensive procedure. Right? You need to, very naive algorithm you can think about is, let's enumerate all the subsets, right? Yeah, that will be the power set of the original set, right? You have an exponential number of subsets to check. And for each subset, let's check if it is a minimal cover, right? Let's try removing each item and see what happens, right? So this computational complexity, if you do it naively, is very high, right? Here, it only has some theoretical significance, right? No one will solve the knapsack problem by formulating the knapsack problem using minimal cover, right? No one will do that. We will still use this formulation here, okay? But here, I just want to give you an idea is, if you can afford to add an exponential number of inequalities, you can have a much tighter formulation. Right? So in practice, what you can imagine is something in between. You have the original formulation, and you add some what is called valid inequalities or cutting planes, like those minimal cover cut, to cut off some of the solutions, and then you start doing branch and bound, right? So in practice, no one used a pure cutting plane or pure cutting plane algorithm to solve an MLP. In practice, something works the best would be a combination of branch and bound and cutting planes. Okay, yeah. Any other questions here? Now, so I still have around 25 minutes. Let me explain sort of a theoretically very interesting concept in integer programming. You probably won't work on this aspect, even if your research is on optimization. But I think it's something good to know, right? So in the next 25 minutes, if you don't follow the math, it's okay, because in order to show all the proof, it could be very tedious. But I just want to show you this concept such that you know they exist, okay? You don't need to worry about all the proofs, but of course, if you are curious, you could check the proof and see why they are true, okay? Now, this idea is the so-called perfect formulation, right? So what does a perfect formulation mean, right? So if you have a set S, which may represent a mixed integer linear programming problem, and you have a set of inequalities, right? And if you can show that the convex hull of this set is nothing but of those linear inequalities, then you see this AX less than or equal to B is a perfect formulation, since it is equal to the convex hull. Right? Geometrically, remember this, we show this like light yellow area and then a dark yellow area, where the dark yellow area is nothing but the convex hull of the integer points, right? So here this AX less than or equal to B basically describe geometrically that dark yellow area that is a convex hull of all the integer points, right? Then if you know the convex hull of the original problem, then the integer program can be solved as a linear program, right? But as you can imagine, getting a perfect formulation for most problem is hard, right? From a computational complexity perspective, you can already see that, right? Since linear programs can theoretically be solved in polynomial time, right? And then we say MLPs are in general NP hard, right? So now you see something is conflicting here, right? If you have a polynomial number of linear inequalities to describe the convex hull, then MLP can be solved in polynomial time. Of course, that's not true, right? So therefore, for general MLPs, if you want to get a perfect formulation, it's going to be very expensive, right? You need exponential number of linear inequalities in order to do that. Okay. So here's another definition of saying a convex set P is integral if P equals to the convex hull of P intersected with integrality constraints. Okay, so basically it says even if you add upon integer constraint and take the convex hull, you still get the original set P, right? So you can imagine if P vertices are all integrality constraint, right? Then you add that integrality constraint and still take the convex hull, it doesn't change. Right? So when is a formulation perfect, right? Or in other words, when is a polyhedral set always have integer vertices, right? So there is a special case called totally unimodular. If a problem satisfies this property called totally unimodular, then all its vertices are integrality constraint. You can just solve that problem as an LP, right? And that's a very special class of problem, right? And then I will explain what totally unimodular means, such that when you encounter a problem and then they say this problem is totally unimodular, you understand what that means. That means even if that is a MLP problem or IP problem, you can just solve it as a linear program, and you always get integer solutions from that. Okay. Okay, so before we introduce the definition, let's introduce some intuition on when will a linear program has integer solution. Right? So remember when we solve linear programs, right? Especially when we use simplex algorithm, remember they are basic variable, non-basic variable. Right? For the basic variable, you take something called basis matrix B, right? And take B inverse times the small b. For all the other non-basic variables, you set them as 0, right? So the idea is if the matrix, the basis matrix have some very interesting property, then this B inverse times small b will be integer. Right? If let's say b is integer, small b is already integer, right? For the sake of the argument, right? So b is n by m non-singular submatrix, okay? And I is a m by m identity matrix. Right? So here's an observation, right? So if the optimal basis has integral entries, and the determinant of the basis matrix B is +1 or -1, then the linear programming relaxation solve the IP. Why is that? Right? Okay, first of all, let's think about how to represent B inverse. Right? So maybe you still remember this so-called Cramer's rule. Right? So B inverse can be represented as the adjoint matrix of B. Right? So remember what sort of adjoint matrix is, right? I think it's related to you remove one row and column and take the determinant, something like that, right? So now with that, if all the entries are integer, right, then the determinant would be integer. Right? The determinant is some functions that you multiply. Pick one atom, multiply with another atom in each row, and so forth, right? So that's why if all the entries are integer, then the adjoint matrix is also integer, right? And then if the determinant of B is +1 or -1, you are essentially dividing an integer matrix by 1 or -1, right? So, and then the B inverse remains to be integer, right? Okay, and then if small b is an integer vector, then B inverse B is integral, right? So that's just a special case where when the determinant of B is 1 or -1, and then all the entries of B are integer, then you can get the solution to be integer, right? Okay. So with that, how do we generalize this idea, right? Because essentially when you take the basis matrix, it can be any subset of the original matrix A that are m by n, right? So the total unimodularity is a general way of describing such matrix, right? So total unimodularity is saying, given a matrix A, it is totally unimodular if every square submatrix has determinant 0, 1, or -1. Right? Okay. So here it shows you an example of the total unimodular matrix. Right? If you take any square submatrix, right? Let's say we take the first 2 by 2. Right? The determinant you can calculate very quickly. It's -1. Right? So it is saying you take any square submatrix, the determinant is 0, 1, or -1. Okay. Then again, I'm not going to the details of the proof. So it says if you have an integer program where A is a m by n integral matrix, then the polyhedral is integral for every B in integer if and only if A is totally unimodular. So that's sort of an important property for a given polyhedral to always have integer vertices. Okay, right. So now there are also some further theorem. Let's just skip that because I want to give you more intuition by showing you an application. But the takeaway here is that there's some property called totally unimodular. If the left-hand matrix satisfies this property, totally unimodular, then you can think about all the basic feasible solutions are integers. Right? And why that is the case? Because due to Cramer's rule, right, you are dividing the adjoint matrices by the determinant of B. Right? If the determinant of B is -1 or 1, then you are essentially dividing integer by -1 or 1, and that B inverse is always integer. That's sort of the intuition, but in order to prove that rigorously, it will need some like very lengthy and tedious proof, right? So we will skip that, and then how do you check the total unimodularity condition? So here it gives you a sufficient condition to check, right? Because in order to check the definition, it is not so easy, right? You need to check all the submatrices, square submatrices of a given matrix, and it can be quite tedious to do, right? So here's an easy to check sufficient condition when a matrix A is totally unimodular, right? Again, I won't be proving that. Actually, proving it is not so hard. You can just check the proof. You only need some basic linear algebra to show that is true. Okay. Yeah. So this sufficient condition is saying all the entries are 1, -1, or 0. Right. That's easy to check. And each column contains at most 2 non-zero coefficients, right? So in other words, you sum over all the absolute value is less than or equal to 2, right? Because they can only be 1 -1 if they are non-zero, okay? And then the third condition is saying there exists a partition of rows such that each column containing 2 non-zero coefficients satisfy this property here. Right? Basically, you can partition the rows, and now you check each column, right? And then the values on the first partition and the values on the second partition in each column are equal to each other. Okay, so let's just assume this is true, right? I'm going to skip the proof, and then I will show you an application where total unimodularity holds, and it has very strong implication. Okay. So that's a very famous max flow min cut problem. Right? You have one of the homework questions on max flow min cut. Okay, so that's for the sake of the argument. Let's first forget about total unimodularity for now, or integer programming for now. Let's talk about what is max flow min cut problem conceptually. Okay, so the max flow problem is to say you have a given graph, right? So you want to send some flows from the source node to the sink node, right? Now you have some directed edges, right? You can think about this as some one-way street, right? You can only send flows from S to 1. You cannot send it back, right? So you have some directed edges, right? And each of the edges is constrained by the capacity D, right? So you can only send at most 5 units of flows from S to 1, right? And similarly, from 1 to T, you can send at most 4 units of flows, right? So what max flow is saying, given the constraints, so let's consider all these edges within this circle here, right? Consider all those edges that are between S and T, right? What is a max flow you can send from S to T? Okay, given those edges have capacity constraints, right? Okay, but in those intermediate nodes, they must be balanced. That means if you send, let's say, 5 units to 2, 2 must also send out 5 units to somewhere else, right? Only the source node can send out net flows, and the sink node can receive the net flows. Okay. Yeah, that's a problem definition here. Okay, so in order to formulate this mathematically, what people usually do is drawing an additional edge from the sink node back to the source node. and set the capacity to infinity. Okay. The reason they want to do that is because by joining a back edge, you can have all the nodes being balanced. Right? Suppose S is sending out some flows, right? And then T is receiving some flows from S, right? As I said, all the intermediate nodes cannot hold any flows. What comes in must go out, okay? Then all the flows that S send out will go to T, right? Because the intermediate nodes cannot hold any flows, right? So then if you have a back edge, then let's assume T will send out whatever S send out back to S. Then S and T will also be balanced, right? Because for all the flows S send out, it must go to T, right? And let's suppose there is a back edge, and then T will send out whatever S send out back, right? Then all the nodes basically will be balanced, right? That's just a trick for this formulation. Okay, so now how to formulate this problem, right? So you can think about the max flow problem as maximizing the flows T sent back to S, right? Because all the node flows sent out by S are received by T. So you are maximizing X TS. Now for all the nodes, because we add this back edge, all the nodes must be balanced, right? So what a node receives must equal to what a node send out, right? So that's why you have, this is like a mass balance equation, right? So chemical engineers are very familiar with mass balance, right? At a given node, what goes in equals to what goes out. And then this is like a capacity constraint, right? For each of the flows, it have to be less than or equal to the capacity, Dij. Okay, and then all the flows have to be greater than or equal to 0, right? So this is so-called max flow problem. Okay. Now, let's talk about the definition of a min cut problem before we do that. Okay. So forget about the back edge for now, right? So what is a min cut problem? So first of all, we need to consider what is a cut of a graph, right? The definition of a cut is the following, right? Suppose you divide this graph into two parts, right? Let's split all the nodes into two parts, right? In total, maybe they are 1, 2, 3, 4, 5. There are 5 nodes, right? Let's split the nodes into two subsets, right? One, 1, 2, and S is in one of the subset, and T and 3 is in another subset, right? So you can split them arbitrarily, right? You can put 3 and 2, and then you could also do 2 and 3, right? So this is a particular split or a particular partition, right? A cut of this partition is to say, let's add up all the edges that are connecting from the left side to the right side, right? So these 3 nodes are on the left side. These 2 nodes are on the right side, right? So suppose they are cut by this dashed line here, right? So now let's consider all the edges from the left to the right, right? So this edge is from the left to right. This is left to right. These 3, both edges are connecting from the left side to the right side, right? Now, if you add up all the weights of this, this is called a cut, right? Because you have a cut and then you add all the weights of these 3 edges, right? Then that is the, let's say, the cost of this cut, right? The min cut problem is to say, let's find a partition such that when you add up all the weights, it is minimized. Right? Okay. So now the total weights is 4 plus 5 plus 3. Right? In total, they are, let's say, 12. Right? And then if you pick a different partition, right? So let's say if we pick this partition, right? 1 S are one side, and then 2 T and 3 are on the other side, right? So what is the value of the cost of the cut for this problem? Right? You need to basically pick. So this edge should be included, right? Since it's connecting, and then this edge should be included. This should be included, and then this should be included. So whenever you choose a partition, the cut will, the value of the cut will change, right? The idea is you want to find the mean cut, right? Okay. Now, without showing you the formulation, do you think this problem is a linear program when you want to solve the mean cut problem, right? Because it involves some sort of partition of graph, right? You may be tempted to define some 0, 1 variable, right? I would formulate as a 0, 1 problem because 0 can determine the nodes are one side, 1 determine the nodes are on the other side, right? Right. So that's a very intuitive way of formulating that problem. But then the very pretty thing about this problem is that it can actually be solved as an LP. Right? So how do we derive that real quick? Okay. And then what is even interesting here is the dual of the max flow problem is a mean cut problem. Okay, so let's take the dual of the max flow problem and see what happens. So let's consider the dual variable for these capacity constraints, right? And then, so you have dual for the capacity constraints, and then you have the dual variable for each of the nodes, right? Like the mass balance constraint. And then after now you should be super familiar with taking the dual. I will just skip this step. And then you will get this formulation, okay? So remember, Wij is the dual variable for the capacity constraint, right? And then Ui, Uj are the dual variable for the mass balance constraint for each node, okay? So now you get these inequalities, right? Ui minus Uj plus Wij greater than or equal to 0, Ut minus Us greater than or equal to 1, all the Wij are greater than or equal to 1, right? So if you look at this problem, it doesn't look that obvious this is a mean cut problem, right? All the variables are continuous in the first place. But then the nice property of this problem is all this constraint matrix is totally unimodular. Right? You could show that using this sufficient condition I gave you. I won't show that here, but intuitively you can think about all the coefficients are 1 or minus 1, right, in those problems. And then you could check the sufficient condition. They actually satisfy the sufficient condition. Right? So for now, you can just believe me, this problem is totally unimodular. Then all the extreme points are integral, right? So the right hand, you can think about the right hand side. All the right hand side parameters are 0, 1, and 0, right? They are all integral. So you can think about all the solution to this problem are integral, right? Now why it corresponds to the mean cut problem, we can show you here real quick here. Okay. So one key observation here is if you replace Uj by Uj plus alpha for all the nodes, the solution will be unchanged, right? So you could think about it that way, right? So if you look at this constraint here, and then Wij is sort of the variable corresponding to the edges in the objective, right? So essentially, all the constraints on Wij are, Wij need to be greater than or equal to Uj minus Ui, right? So Wij need to be lower bounded by the difference of Uj and Ui, and then you are minimizing over Wij, right? So here you are minimizing, and D is greater than or equal to 0, right? So this gives you a lower bound on Wij, and of course you want if you only have this constraint, it will take the value of this, take this value, right? Because you are minimizing. Okay. Then if you scale the Ui and Uj by alpha, it doesn't change the bounds on wij, right? If you add alpha to all the ui uj's, right, their difference won't change. Okay, so therefore, without loss of generality, you can pick a reference, right? Just set us equals to 0. Okay, so if you set us equals to 0, then here you have ut greater than equal to us plus 1, right? So basically ut is greater than equal to 1. Okay, so now the proof is a little bit subtle. So you already know that all those extreme points are integrality constraint, right? So now let's consider two types of nodes, right? The nodes where the uj's are less than or equal to 0, and the nodes where the uj's are greater than or equal to 1, right? Since all the u's are integrality constraint, this is like a partition of the nodes. Okay, and then of course the source node will belong to this particular set since we set it to 0. Okay, so now we have these two inequalities correspond to the objective function, where the objective function is the sum of dij, wij over all the edges, right? Over all the edges in the graph. Okay. Now the first inequality will hold where we pick all the edges in the graph, but the first node has to be in the set X, and then the second node has to be in the set X, X bar. Okay, so as you can see, this summation is sort of a subset of this summation. Right? You are reducing the number of edges that are in this summation because you add more constraint on A and J. Okay, so with that, why this hold? Because wij is greater than or equal to 0, and then dij is greater than or equal to 0, right? If you have a subset of the summation, it should be less than or equal to the original objective. Okay. Now, yeah, so that's why the first inequality hold, and then the second inequality hold because the wij is greater than or equal to 1, right? Because if the first node is in this set and the second node is in that set, then they have to be different by at least 1, right? Because those u's are less than or equal to 0, those uj's are greater than 1, and then wij has to be greater than or equal to uj minus ui. They has to be at least greater than or equal to 1, right? So then if you replace those wij by 1, this inequality still hold, right? Since wij is greater than or equal to 1. Okay, so therefore this is a lower bound of the original problem, right? So this is the lower bound of the original problem. But then if you can show there exists a solution that obtain this lower bound, then it is a feasible solution, right? Okay, so the way you can show that it is a feasible solution is just set all the uj's to 0 in the set X and all the uj's to 1 in the set X bar, right? And wij equals to 1. And then you can show that that's a feasible solution to that problem. Essentially, from a physical perspective, this set will be the set corresponding to the source node, right? This set is on one side of the cut, the other set is on the other side of the cut. Right? You use this inequality trick to show that the solution you constructed that way is a lower bound and it is feasible. All right, so that's why it is a min cut. Okay. If you are curious about it, you could read about the proof in a bit more detail. But the takeaway here is totally unimodularity is an interesting property, right? Some very special problem satisfy this property, like the min cut problem. Then you don't need to enforce integrality constraint. in those problems. Right? I mean, intuitively, if you don't know totally unimodularity, one would be very tempted to define 0, 1 variables for the min cut problem, right? Since they deal with whether the node is on one side of the cut or the other side of the cut. This property shows that even the problem is formulated as an LP, it always gives you integrality solutions that correspond to the optimal solution of the min cut problem. Okay, so if you want to read a bit more, there are a few references, especially the last 2 references on integer programming.